15 times a second for 30 seconds, well, you just call the scheduled function with those parameters, and it would automatically turn on and off the lamp at the appropriate time. So, like I said, you don't need to pay attention to all the intricate details to write code for this thing. The last function is called a pitter-patter, which, as the name kind of implies, it'll turn on and off a driver repeatedly, indefinitely, until you tell it to stop specifically. So the next control system are switches. As you know, switches are fairly important in a pinball machine. And we support 32 direct and a full matrix. Some WPC machines use up to a 9x8 matrix. Stern machines, I believe, use an 8x16 matrix. So we support all that. Like I said before, the P-ROC automatically scans the matrix for you. It's configurable how fast it does that. You can configure all the way down to a 1 millisecond scan rate. Why you'd want it slower, I don't know, but the option is there if you want to. And the way it works is while it's scanning the switch matrix, it recognizes when a switch changes. Say a switch goes from open to closed or closed to open. The P-ROC sees that change, and then it needs to know what to do with it. And what it does with it is totally programmable. So for every switch that you use, and every state transition, open, closed, and a couple of debounced states, for every single one of those things, you can individually program a rule to tell the P-ROC what to do with that switch change. The two main options are notify the host, so tell your software, send a signal out over the USB cable saying the switch changed from open to closed. In fact, it was switch number 32 that changed from open to closed or whatever. The other thing you can do with it is automatically reconfigure a driver. So you can have the P-ROC say, switch 12 closed, let me automatically assert coil, turn on coil 10. Why would you want to do that? Well, because we're using a USB connection to the computer from the hardware, there's some time it takes to get that state transition from the machine to the software, process the change, and then update your hardware with whatever it is you want to do. So for something like a flipper or a pop bumper, maybe a slingshot, you want those things to react immediately. So you would probably configure your flipper buttons to automatically drive the flipper coils, and vice versa. You'd program them so when you release the flipper button, the coil's turned off. Same thing for slingshots, same thing for pop bumpers. Anything that you need to react in real time, you would want to use one of these rules for. And there's a link to additional rules, so you can set up a whole chain of events that happen each time a single switch occurs. I don't know why you want to, but you could set it up to, you hit the flipper button and all the flashes or all the coils or all the lamps go crazy. It's all software at that point. You can do whatever you want. We support a DMD. It's the P-ROC controls all the digital signals that go to the DMD. So we take care of all the timing and all the logic to drive a dot matrix display. We support a bunch of geometries of DMDs, but obviously the standard is 128 by 32. The hardware has support for frame buffers, so you can keep your animations running smoothly. It can drive up to 16 levels of dot intensity, so you can try to get 16 colors out of your display. It's got a programmable frame rate if you want to sync it up to 24 or 30 or 25 frames per second because you're trying to show a movie on your DMD for some reason, that you're trying to integrate some movie clips from your favorite theme on your machine. You can program the frame rate. And we also, just like we have switch events that go back to the host to tell your software when switches occurred, you can set up the dot matrix logic to tell you when a frame was displayed. And you do this in order to synchronize your software with the hardware so that everything knows exactly when the frames are displayed. So again, you can keep your animations running smoothly or keep everything synchronized. And the last piece of the thing that the hardware supports or drives is an auxiliary bus. On WPC machines, this is used for the alphanumeric displays. On Stern machines, there's a bunch of machines that use the auxiliary bus for LED features on the playfield, or I know there's a scrolling LED display on games like Wheel of Fortune, or World Poker Tour has an LED matrix on the playfield. And those are all connected to what's called an auxiliary bus. And the P-ROC does support that. You can write code to drive all these things as well. Lastly, kind of a summary, there is a USB interface on the board. It's used to get events from the board down to your software, and when you update your drivers and your lamps, your dot matrix display, all that stuff goes back through the USB cable. And essentially what this does, it allows you, when you're writing code for when you're writing custom code for your machine, you don't have to worry about all the low-level details. The P-ROC controls the hardware, and it does it automatically. So really, all you have to do is worry about writing your game rules, which is probably why you started the project to begin with. So that's it for hardware. I'll pass it over to Adam, who will give you an insight into the software.
Thank you, Gerry. I just want to come up here and say thank you, Gerry. All right, so I'm going to talk to you all about, my name is Adam Preble, by the way, and I'm going to talk to you all about the software options that we have for you for use with the P-ROC project. There's quite a few of them, and so let's get to it. So what's actually available right now? We have something called libpinproc. That's a C library that allows you to talk directly to the P-ROC hardware. And this is a really low-level one-to-one mapping from the features of the P-ROC directly to the software API. So you're not really, we haven't made any assumptions about the way that you want to control it. It's just you're using it directly. And as it says there, it's in C, so you can pretty much get access to that in, I would guess, most any language that supports some sort of extension mechanism, such as Python. So we also wrote pyprocg, which is a wrapper for libpinproc. It essentially exposes all the functionality of libpinproc to the Python language, which if you're not familiar with it, it's kind of a higher level, well, significantly higher level language than C. And what that means is that you don't have to do quite so much dirty work. You don't have to mess with pointers, memory management's handled for you, and so forth. And we thought that'd be a nice language to use for writing pinball software. And then the last one I want to mention here is pyprocgame, which we're going to be spending the bulk of our time talking about. And it's a high-level framework, and as you can tell by the pi prefix, also written in Python. So all three of these work together. pyprocgame is built on top of pypinproc. pypinproc goes on top of libpinproc to provide you kind of a full stack, if you will, for writing pinball software. And I guess I should mention that pyprocgame is different from pypinproc in that it's higher level, so it's much more focused on how you want to implement the rules of your game, how you want the display to work. It has a lot of helper stuff to make that a lot smoother. And and I should mention that Python's a great cross-platform language, and C can be made to be cross-platform as well, so you can run on a Mac, Windows, and Linux. And the whole point here is that you can choose whatever level that you want to interact with P-ROC at. If you don't like the way that we wrote pyprocgame, then you can interact with P-ROC at a much lower level. Or if you really want to, you can get into the FPGA spec and issue buffer commands. But I don't know if I'd recommend that. So why do we choose Python? As it says here, all the answers are spelled out, but it's cross-platform, it's high level, so it's much more accessible to people. It has some cool introspection features which we make use of in pyprocgame, and it's pretty fast. Certainly not C fast, but it's pretty fast. So what does pypinproc look like? So here's a line of Python code. We're going to import the pinproc module. So that just means that we're just kind of loading a library here. And then within the pinproc module, we have this object called pinproc with some capital letters. And you can see that we're passing it WPC. So we're telling the pinproc software and the P-ROC hardware, I'm interacting with the WPC system. Set up all your defaults for driving WPC-style coils and the WPC-style switch matrix. There's also the two Stern varieties and WPC95, and also a custom machine type that doesn't do any sort of setup for you, so you can set up how